So I'm really very pleased to welcome Dr. Simone Brugiapaglia. And I welcome you all today too. The topic today is the mathematical foundations of deep learning, from rating impossibility to practical existence theorems. So why the deep learning algorithm continue to show impressive performance in a wide variety of applications? Can we understand the cases where the performance of this algorithm are limited? And so these are the question that Dr. Simone Brugiapaglia asked, and they are fundamental questions. So Simone is assistant professor at the Department of Mathematics and Statistics at Concordia University. He studied mathematics at the University of Pisa in Italy, and he received his PhD in mathematical models and methods in engineering from Politecnico di Milano in 2016. He was a postdoc fellow at École Polytechnique Fédérale de Lausanne in 2016, and at Simon Fraser University from 2016 to 2019. In 2019, he was awarded the Leslie Fox Prize for numerical analysis by the Institute of Mathematics and its applications. He has co-authored several scientific publications, and his research interests include mathematics of data science, computational mathematics, and numerical analysis. So thank you very much, Simone, for joining us today.
Yeah, thanks. Thanks, Habib, first of all, for the invitation, and very, very nice introduction. It's yeah, I need to get used to to have the list of things about me said before the talk. Yeah, it's really kind of you. So yeah, the Habib nicely introduced the theme. So first disclaimer, maybe that's going to be that I'm coming from mathematics and statistics department. So of course, you might expect it's going to be a pretty mathy talk. But feel free to interrupt me anytime. If something doesn't make sense, I will try to introduce notation and definitions. But I'm happy to take questions also during the talk. Don't wait until the very end if there's a burning question. So before starting, I would like to acknowledge collaborators for this projects that we'll present today here. They are from Concordia. Matthew Liu was an undergrad student. Now is working for Ubisoft here in Montreal. Nick Dexter is assistant professor at Florida State University. Ben Adcock, Paul Tupper, they were my postdoc mentors. Simon Fraser University, and Sebastian Moraga is a PhD student there. Clayton Webster is a distinguished researcher at University of Texas at Austin. And of course, I would like to acknowledge the various sources of funding that made this research possible throughout the year. So Answer, Concordia, the CRM, and the Pacific Institute for the Mathematical Sciences. Okay, so there was a quote in my first slide. You might have read it. So if you cannot see it very well, I'll read it for you. Get ready to delve into the mind-bending intersection of mathematics and artificial intelligence, where elegant equations and concepts lay the foundations for the miraculous advancements in deep learning that are transforming our world today. These are not my words. This is a quote. Have you ever seen this? Like, anyone knows who is the author of this quote? And you can guess? Hint is not human. ChatGPT, yeah. So that's just, I asked ChatGPT, write a brief opening sentence for a seminar on the mathematical foundations of deep learning, made it exciting and mind-bending. That was the output, pretty nice, I would say. So the success of AI these days, the way technology was pushed to kind of have this kind of very cool results, it's very impressive. We are, it's now really part of our daily lives. And of our students who now look for solutions to assignments on ChatGPT. So it's pervasive on our daily lives today. And we live in a so-called AI golden age. If you look at the data, this is taken from the 22 AI Index report of Stanford. This is the number of publications in the last, so from 2020 to 2021, in each subfield of AI, so there's like pattern recognition in black, machine learning in blue, computer vision, purple, and so on. So the blue curve is pretty impressive. So on the y-axis, we see number of publications in thousands. So in the machine learning, there's a very steep increase. So the amount of research being done in this field is really impressive. It's hard to keep up with the literature. There's an impressive amount of research being published. And we have seen all the breakthroughs in the recent years from AlphaGo, game playing. These were all breakthroughs within machine learning that were due to the so-called deep learning that I will tell you more about. I will define, what we mean by deep learning. But that's a particular component of machine learning that kind of made possible very, very big leaps forward in several fields, like AlphaGo, game playing, or speech synthesis, Apple Siri, or Amazon Alexa, Netflix recommender system, and so on. Like the latest one is ChatGPT that everyone now is talking about. And that's great, but like every story, there's the other side of the coin. There's a lot of skepticism too around deep learning, a lot of concerns, like there's this field of adversarial attacks on deep learning that kind of reveals that deep learning algorithms can be deeply unstable. You can fool, so to speak, deep learning algorithms, for example, when you perform computer vision, and your deep learning-based computer vision algorithm is trying to recognize its signs in the road. So then you can fool it to, instead of recognizing the stop sign, is a go-ahead sign. And now if this is part of the engine of a Tesla autopilot, this can be deeply problematic, as we see. So there's many articles kind of talking about all these issues, both practical and theoretical. These kind of instabilities can also be analyzed from a theoretical viewpoint. That's a recent paper, more on the math side, published in Science News, about the fundamental limitations of deep neural networks. And so in this picture, we're like, on the one hand, we see very exciting results. On the other hand, we see a lot of kind of fundamental questions not being solved. I think it's crucial to kind of shed some light and study these techniques from the mathematical perspective. So that's kind of the motivation of the talk. And I want to go even a couple of decades back in time with this paper by Steve Smale, 98, Mathematical Problems for the Next Century, where already these kind of issues were being discussed. So this was a paper written after a request of the then Vice President of International Mathematical Union, Vladimir Arnold. He asked several leading mathematicians in the world to kind of give a list of meaningful mathematical problems for the 21st century, inspired by what Hilbert did for the 20th century, the millennium problems. So Smale's list has both pure math and applied math problems. The very last problem is a very applied problem, a very big problem, very challenging problem. Problem 18 of the Smale list, limits of intelligence. What are the limits of intelligence, both artificial and human? That's a very broad question. Possibly, this opens whole fields of research. But what I like is really this paragraph within the description of the question, where Smale says a broader study is called for, one which involves deeper models of the brain and of the computer in a search for what artificial and human intelligence have in common and how they differ. And that's what I really like. I will look into a direction where learning, problem solving, game theory play a substantial role together with the mathematics of real numbers, approximations, probability, and geometry. So already here, there's a lot going on. Smale is hoping for this highly interdisciplinary approach to tackle this difficult question. And what I find visionary of this particular paper is that that's what ended up happening here. We are actually now witnessing a lot of people from mathematics, both applied and also pure math, actually, coming to this field because the question is so hard that you really need this approach that combines sometimes probability, linear algebra, analysis, as we will see today too. So yeah, motivated by this context, the goal of this talk is the following. We will try to understand potential and limitations of deep learning through rigorous mathematical approach. And to do this, I will suggest two case studies. So they're kind of different in nature. The first one is the problem of identity effect classification. Will be a classification task. And in that case, I will show you some recent theorems about limitations of deep learning called rating impossibility theorems that I proved with some collaborators. For the second case studies, will be more on the positive side, and it will be called practical existence theorems. It will be theorems about what can deep neural networks do. And the context would be different because in that case, the problem of interest would be high-dimensional function approximation. So again, these two case studies differ in the motivation, in the outcome, because one is potential, one is limitations of deep learning, also differ in the tools. The first one, I will use pretty elementary math tools to develop the theory. It will be just basic probability, linear algebra, like numerical linear algebra, but nothing much more. In the second one, there will be more kind of using pretty advanced tools that were developed over decades to put together a theorem about deep learning. There will be compressed sensing theory, there will be deep neural network approximation theory, and so on. So keep in mind this, these two parts are kind of independent, but I wanted to showcase both because I think that also conveys the message of like how diverse the research in this field can be, and how different tools can help you kind of understand different types of questions. Okay, I've been talking about deep learning a lot, so let's actually define what do I mean by deep learning. I'm sure perhaps, almost everyone perhaps already heard these two words, but now we'll actually, at least to fix notation, to make sure that everyone is on the same page, let's define things. If you Google deep learning on Google Scholar, you'll find more than 5 million hits. It's a jungle. It's really easy to get lost, especially for students. Those who want to start to understand what's going on in the field and are interested in a more rigorous approach, there's a lot of computer science related literature. But on the math side, I highly recommend this paper from Simone Review, Deep Learning, an Introduction for Applied Mathematicians. It's really clearly written, self-contained. It's a gentle introduction with a good amount of rigor in it. If you're curious about the history side of things, there's this review paper by Schmidt-Huber called Deep Learning in Neural Networks, an overview. The history of deep learning is very interesting and controversial. Dates back decades ago. The very, very first ideas can be traced back in around like the 50s. So it's very interesting, even seeing the evolution of this field. But now it's kind of mainstream, and a lot of people are working on it. But the early ideas are date back in time quite a while. So yeah, what is a deep neural network? So deep learning will be about training deep networks. The way I think about deep network is just about a function approximator. In this case, it is a so-called feed-forward deep neural network. You have an input variable x. You propagate, so you apply an affine transformation A naught. Affine just would be linear piece plus a translation here, wkx plus bk. You apply this linear transformation. You apply a nonlinear so-called activation layer, which typically is something like the so-called ReLU, rectified linear unit function, or the hyperbolic tangent function. And that's one hidden layer. And you propagate the signal like that for different hidden layers. You just alternate affine transformation with nonlinear activation and so on. And you arrive at an output that I will call phi of x. Okay, so some notation. The number of hidden layers here will be denoted by capital D. That's the so-called depth of the network. That's why deep learning. And people usually, you might see, graphs. Why are they called networks? There's no network in the first line. But actually, if you interpret these linear algebra operations here with a graph interpretation, also like the matrix vector multiplication, you associate, that will give you connections between the entries of the input vector and the entries of the output vector. If you do that interpretation, you can build a graph that is a network out of this approximator. And so you can imagine your input here in red being propagated through these green hidden layers in green, and then coming to the output layer at the very end in blue. And that was, by the way, the initial motivation, because people wanted to model the brain that is a network of neurons. So here the neurons will be all the entries of this input and the hidden layer vectors. Okay, so a bit of notation. I will talk about architecture. That's just all the parameters defining this approximator. So the size of the input, of the hidden layers, of the output layer, and so on. The choice of activation, sigma. The depth, as I said, is the number of hidden layers. And so trainable parameters. So now there will be some learning involved, or in other words, some training. All the parameters defining the affine transformations here, wk, bk, will be trainable. So we'll set up some optimization in order to fit the data. So fit the parameters to some data we have. Okay, so deep learning, this is deep neural networks. Deep learning involves training. So you have some sort of optimization function to find the optimal trainable parameters. typically will be composed by a loss function that is a data fidelity term, plus a regularizer that might enforce some extra structure on the trainable parameters. For example, if you are doing regression, you might have a least squares type loss function. It's just, so now if your data set is xi, yi, you just measure the distance between the predicted output by the network here and the actual data yi with respect to the classical L2 norm here. It's a sum over just residual squares. If you're on the classification setting, you could use loss functions like the cross entropy. That's very popular in computer science. That's appropriate when the data is composed by classes. Okay, so maybe like image classification, this is an image of a cat, of a dog. So you will have, instead of quantitative variables yi, you'll have qualitative variables yi. Regularization terms, typical choices could be the L1 or the L2 norm of the L2 norm squared for of the trainable parameters. In the first case, L1 norm, that gives you so-called lasso regularization. For example, in the L2 norm, sorry, there should be a power p here, so L2 norm squared, that will be Ridge type regularization. Okay, this is just an optimization problem. And how do you solve it? That's the training phase. You need to find the optimal parameters. This could be very challenging to solve because, this network is a very nonlinear object. This objective function will not be convex, will not have all the mathematical properties that we like and that we allow us to do theory. But in practice, what seems to work is some kind of stochastic optimization strategy. So one of the first strategies is so-called stochastic gradient descent. And the idea is simply to essentially divide the data set that is now here. M is the number of data points into batches, B0, BK minus 1. And then you restrict your loss function here on the current batch of data, and you perform a gradient descent step, only considering the loss function associated with that subset of batch, the small batch of data. So when you iterate over all the batches, that's called an epoch of learning. Okay, that's a bit of terminology in the optimization world. That would just be an iteration. It's called an epoch because you visit the whole training set, and that gives you, so where you do the second pass over the whole data with the second epoch, and so on. Okay, so that was the crash course on deep learning. What the meaning of all the things I would be talking about is, and a bit of notation that I need to talk about the theory. So now let's delve into the first part of the talk, the first technical part, which is the rating impossibility theorems, the first project, where we'll focus on the limitations of deep neural networks. Before I move on, maybe any question about the setting? Everyone's on board? Hopefully that was not too trivial or not too obscure. I don't know. Hopefully something in between. Okay. Question for you. Now this very intuitive thing. Assume that I tell you the green words are good, AA, GG, LLMM. The red words are bad, AGLM, GLMA. Now I ask you, are YY and YZ good or bad? And people online can type in the chat if they wish. Who thinks that YY is good? Who thinks that YY is bad? Okay, many people abstain, but the majority was thinking that YY is good. Okay. Who thinks that YZ is good? Who thinks YZ is bad? Right. Okay, there seems to be a consensus because for humans, it's a pretty easy task. You were just asked to recognize if two objects are identical or not. Okay. So two-letter word, is that formed by two identical letters or not? So that I will call this an identity effect. That's a task. That's a classification task. Given a training data that I give you at the beginning, that was the training data, the green and red examples, and the test data was the black thing. Like I was testing your learning on new data that you never saw before, by the way. So you were generalizing the task in machine learning jargon. You never saw Y or Z in the training set, but you had no problem to kind of understand what the pattern was and generalize it. I could give you two new symbols that don't even exist in any alphabet. You will still be able to generalize this task very easily. There's something going on in the human brain that makes generalizing this task kind of straightforward. And the question will be, can machine learning algorithms do the same? Okay, can they generalize this type of seemingly very simple task? Well, that's a question that was originally motivated in linguistics, because these kind of structures arise in like when you want to understand if a sentence is grammatically correct in a certain language, so syntax, or if you want to understand if a word is possible in a language in phonology, if it's phonologically possible. So these kind of patterns will tell you if certain words are allowed or not. And then there was an experiment in 1999 by Gary Marcus, who, by the way, wrote a really cool book called Rebooting AI, about like discussion problems and potentials of AI. It was published, I think, 1 or 2 years ago. I highly recommend. It's really nice and kind of accessible reading. In 1999, Gary Marcus did this experiment. It showed that 7-month-old infants can generalize this type of rules that I was showing you before. There were experiments like with sounds, and infants were supposed to react differently when the sound was structured in a certain way or not. And they were proved to generalize, even if they're not able to speak or, or to perform other very simple tasks. And then he also showed that if you try to train a neural network on this task, you fail. It was not able to train it. And that's gathered a big debate. So like that debate was like, can then neural networks be really assumed to be a good model of the brain or not? There was this debate between connectionist people who thought, yeah, the brain is actually a neural net, and maybe we're just not training them well enough. We're not using the right algorithms to train them on this kind of task. Other people, maybe the not connectionist people, were thinking, no, there must be something else going on in the brain that is not just connections between neurons that allows this kind of generalization. This debate again dates back to the 90s. There's very kind of heated back and forth in the literature. Is pretty fun to read. Even in 2020, some of these debates still happens. Now it's been evolved quite a lot, but like there's a nice debate by Professor Joshua Banjo, Université de Montréal, right here, who was awarded the Turing Award for deep learning in 2021. I don't remember now, or 2020. And Gary Marcus, it's really nice. It's on YouTube. So Google it if you're curious. There's still debate about this kind of fundamental generalization issues and other topics. So we wanted to address this question formally. So can machine learning algorithms learn this or not? Let's try to put some math here and try to solve this question. We need some notation as usual in math. So I will call calligraphic X the set of admissible inputs. And here we have 2-letter words. So for example, X can be all the set of possible words like AA, LM, YY, and so on. We want to assign a rating to each word. That will be a number between 0 and 1. That will model the probability that that word is good or bad. Okay, so bad will be 0, 1 will be, good will be 1. And if you're not sure, maybe 50%. Typically, the machine learning algorithm will give an output which is not necessarily 0 or 1, will be something in between, which means how confident the algorithm is that this is good or bad. The training data set that I showed you at the beginning looked like this. It was telling you AA is good, so AA1 is one pair of the data set, GG1, and so on, AG0. And then the learner. So for this part of the project, we use this notation because I think it captures a fundamental behavior of kind of the generalization capability of a machine learning algorithm. So we'll think about learners with this calligraphic L symbol. And the learner will just be a mapping that will take a data set, D, a new input, and it will assign a rating. So at the beginning, I gave you the data set, D, of examples I showed you, good, bad. I gave you a new input, YY, and you were assigning a rating. Okay, so you were the learner in that case. In practice, could be a neural network trained with stochastic gradient descent or whatever, your favorite deep learning algorithm. So first you can prove this very general theorem, so general that might seem useless, because the question will be, okay, can this actually be applied? The theorem goes as follows. You have a data set D, a transformation of the inputs, tau, that realizes the following two things. If you apply tau to the whole data set, that leaves the data set unchanged. So we call that invariance of the data to the transformation. Second one is invariance of the learner. If you apply the transformation to both the data set and the new input, the learner doesn't notice this, and it will give the same rating as if you just plugged in D and X. If these two things apply, then you have that the learner will always give the same rating given the data set D to tau X and X. So this is a theorem that's kind of, we're building this transformation as a way to fool the learner. So this is a particular device that allows us to construct a counterexample where the learner will never be able to distinguish two objects, tau X and X. And the proof of this theorem is ridiculously short. I'm really happy about that. It's one line proof, the shortest proof I've ever published in the paper. You just apply the two properties. So I can even show it to you here. You apply learner to the data set in tau x. You use the invariance of the data. So you replace d with tau d. You then use the invariance of the learner, and when you have tau in both arguments, you just get rid of them. And that gives you the claim. Okay, super easy theorem. But now the point is almost a tautology, if you want. But the point is, okay, when does assumption 1 and 2 are satisfied? Are these reasonable assumptions? Are there examples where we can actually check that this holds? Is there a transformation that does the job? So that was where things get trickier. And I want to talk about the invariance of the learner part before. So first we have another theorem where we apply this to prove that certain learners are invariant to certain transformations. And these learners arise from popular machine learning algorithms. So, okay, the setting will be the data set xi, ri, the rating. And now we assume the learner to be of this form. So like a neural network, phi, that I was denoting before, the output will be the rating. And now I'm using this. The input is x. The first operation you're supposed to do with x has to be a linear transformation by w. And then you can do something else that involves other trainable parameters b. This includes, in particular, feed-forward neural networks, but can be more general. Really, the important feature of this model is that the first operation has to be linear. Then you're free to do whatever you want to do. So if you use a learner like that, and if you train this learner via stochastic gradient descent, particularly if you use k iterations of stochastic gradient descent by minimizing a regularized loss function like the one I was showing at the beginning. And here we don't have particular restrictions of the loss function. For example, f can be really anything as soon as the whole thing is differentiable. And by the way, if you're outside the not differentiability case, there are things that you can do too there, like with the subgradients, but that's more technical. So assuming for simplicity that the whole thing is differentiable and that the regularization term is of this form, so that's the real kind of thing that we need here. We're allowed to regularize the trainable parameters that multiply the input as the very first thing, only using the so-called Frobenius norm, which is just the sum of the squared entries of the matrix on the square root. That's the Frobenius norm of a matrix. You can only use that or can avoid regularizing. For the other trainable parameters, you can do anything as soon as the whole thing is differentiable. So if you do that, if you train this kind of potentially neural network learner with SGD and potentially with regularization, and if you initialize these trainable parameters in a nice way, so in particular, if you have independent random initializations of it, and that's very common in practice, you just, since the optimization problem is so difficult, typically people just provide a random initialization and optimize from there. And that's a more technical assumption. You need invariance of the second trainable parameters w, the initialization, to write multiplication by t. So now, what is t? T is an orthogonal matrix. So we're assuming that the transformation tau now is not just anything, but it can be represented by an orthogonal matrix. So these are the big assumptions here. Tau is not just any possible transformation, is linear and is orthogonal. And tau does this job to the initialization parameters. And this can be actually verified when you initialize the trainable parameters with centered IID random Gaussian variables. This happens. Okay. So it's not an unreasonable assumption. Under this, the learner that is trained with SGD and under this framework will be invariant to this tau in distribution in this case, because there's several objects that are random. So in this case, the invariance, by what I mean by this symbol is that the distribution of the rating on the left-hand side here will be the same as the distribution of the rating on the right-hand side. So this theorem, in a nutshell, shows that invariance of the learner under SGD training is possible. Actually, there are contexts that are quantified here where that happens every time, no matter, and that's the interesting thing, no matter how deep your network is, because a lot of people were saying, okay, depth can help learning more difficult tasks. In this case, you see depth never shows up here. It's not even a parameter. You can have 1,000 layers. It will not matter for this theorem. Also, how many iterations you use of your SGD training doesn't matter for this theorem. This is just generic. k iterations will be applicable no matter how much you run your optimization algorithm. And this can be generalized to other training algorithms. A very popular one is so-called ADAM, adaptive moments, and other models, not only feed-forward neural nets. For those of you who are in the field and know more, like you can generalize this to so-called recurrent neural nets, particular so-called LSTM, long short-term memory neural nets. Anyways, that's more technical. So that's the first half of applying that theorem, invariance of the learner. Let's talk about invariance of the data. Because remember, there's two assumptions here for applying the general theorem. We need both invariance of the data to tau and invariance of the learner to tau. The second thing we did, let's take a look at the first one. Now let's go back to the initial motivating example, and I will define a specific tau here. Remember, the motivating example, your input is a two-letter word. Now I will build the transformation of a two-letter word as following. It has an explicit definition. If you apply tau to a two-letter word whose second letter is a Y, then tau will replace the Y with a Z. If the second letter is a Z, tau will replace the Z with a Y. In all the other cases, tau will do nothing, okay? Just switches Y and Z if they're in second position. So this tau, of course, will leave the training set invariant. Remember, if the training set doesn't contain Y or Z, well, then in the definition of tau, you're never in these first two cases. So you never switch anything. You're always in the identity case here. You leave all the words unchanged. So if you apply tau to the whole training set, where you don't show Y and Z to the learner, tau doesn't do anything. So the invariance of the data is there. But let's take a look of remember, we need an orthogonal transformation to apply this theorem, the invariance of the learner. Is that reasonable? When this tau will be associated to an orthogonal matrix? Well, the story becomes more delicate here. That will depend on how you encode the letters. Because remember, the letters, I mean, now they're abstract objects, and telling you letters, A, B, C, D, and up to Y, Z. How do you store them in memory? That will be vectors of some kind. That will be numbers. So depending on how you encode the letters, tau will have different properties. You will be able to represent that tau as a matrix after you encode letters as vectors. So for example, let's say that we encode letters in R26. If you use the very popular so-called one-hot encoding, that means just A is the vector 1, 0, 0, 0, 0, B is the vector 0, 1, 0, 0, 0, and so on. You just have 1 in position J for the jth letter. That's the one-hot encoding, or also the canonical basis in linear algebra terms. Well, if you write that tau with respect to that basis, T is just a permutation matrix. So it's more than orthogonal. It's orthogonal, but only realizes a permutation of the coordinates. If you use to encode an orthogonal basis, well, tau is not a permutation anymore, but it's going to be orthogonal. So now each letter can have all the entries filled up, but now A is orthogonal to B, which is orthogonal to C, and so on. Pairwise, all the letters have to be orthogonal in the encoding space. On the other hand, if you only have, for example, linear independence, but you might have non-orthogonality, then tau might not be orthogonal, could just be invertible. So our theory applies to these two cases. So the impossibility theorem here, the rating impossibility theorem, where you always prove that the learner will assign the same rating no matter what to two different inputs, will be applicable if you use the first two encodings, will not be applicable if you use something else. That doesn't mean that the learner will be able to generalize, just means that our impossibility theorem doesn't apply, so we don't know. There is room for possibility, so you will have to see kind of numerically what happens. So in our example now, what does it mean for the learner to give the same rating to tau x and x? Let's take a look back to the initial example. If now your input is the word yz that I showed you at the beginning, then tau x will switch the second z for a y. So now tau x is transforming a bad word into a good word. So it's fooling the algorithm. So you will always assign, no matter how deep your network is, no matter how much you train with SGD, you will always be stuck with assigning the same rating to YY and YZ. So provably, any learner constructed in that way will never generalize that task. Okay, so we can check things numerically here, validate that the theory can also be observed in practice. Here, I'm showing what happens if you train a feed-forward neural network with SGD using the one-hot encoding on the first row, an orthogonal encoding called the HAR encoding. It's just a random orthogonal encoding, and a so-called distributed encoding. So the distributed encoding just activates k random bits. So it puts k once in your 26-dimensional vector in random positions. So you don't have necessarily orthogonality there, because you might have for different letters a 1 in the same position, and that will break orthogonality. So in the first two cases, for the first two encodings that fall within the framework of our theory, we observe that impossibility in practice too. So from left to right, we're considering deeper and deeper networks. They're not super deep, but you can go deeper. The things will not change. Here we have 1 hidden layer, 2 hidden layers, 3 hidden layers. The first two histograms, so the y-axis is the ratings associated with the word. Yeah, so it's not very, very large here. Maybe I can zoom in a little bit. The first column is the rating assigned to the word AA, which is in the training set. Here, the training set in this kind of experiments was randomized. So this is the first, oh, sorry about that. This is the first, I have to revert. This is the first bad word in the training set. So this is the training error, how well the learner does on the training set. On the other hand, here we have test examples. So we never show Y or Z. So we test how well the learner is doing on words that are containing Y or Z. And so you see, on the training set, we do pretty well. You know, the good word has a rating close to 1, the bad word close to 0, and it's even better if you have more layers. But then outside the training set, all the ratings are around 50%. That means that the learner has no idea if that is a good or a bad word. It's just assigning random ratings. Okay, so this with the depth, a similar thing happens again on the test set, around 50%. There's no pattern here. For the second example where we have orthogonality, is the same. Interestingly, now for the third example where we break orthogonality, you start seeing some form of generalization. It's not perfect, but now a good word YY is given a better rating than Y0, ZY. Again, we are far from like 100% or 0% here, but some structure starts emerging. So there seems to be some possibility to generalize if you're careful with the encoding. So that's the main takeaway of this part. Like, you need to be careful if you're trying to recognize some kind of pattern. You need to be careful on how you encode the objects, because that will have a crucial effect on if you'll be able to generalize the task or not. So in the interest of time, I will not show another example that involves images, so that we did another experiment. If you're curious, I can tell you a bit more at the end or maybe offline. When you compare, you classify pairs of images of handwritten digits and try to recognize if they belong to if they represent the same digit or not. You can see the same type of behavior, but then here, interestingly, you have to concatenate two models: a computer vision model that recognizes the image and gives like just a vector of probabilities. Like, for example, this is a 9 with probability, with high probability, for example, or 8. Here, this could be a 3 or a 5. So that's the computer vision problem. And then once you have these probabilities, you try to see if they represent the same digit or not. So what you can observe here, without telling you too many details, is that if you overtrain the computer vision model, that will make the job of the identity effect model more difficult, because when the computer vision model does really well, it means that it will predict with high certainty which digit one image is represented. So the encoding will be closer to the one-hot encoding, which is bad to generalize the identity effect. So we observe this kind of behavior. Instead, if you undertrain the computer vision model, so the computer vision does a kind of a worse job at classifying each individual digit, but somehow you can check that it's the performance of understanding the identity pattern will be easier for the identity effect model. So in a way, if the learner is focusing too much on the details, it will lose the big picture. If it's kind of a bit sketchy on the details, but that will grasp the pattern more easily. So there's even a bit of a philosophical message here. So yeah, there's a hand raised. Oh yeah.
Do you want to answer the question?
Yeah, for sure. Yeah, let's see. Oh yeah, there are questions.
Yeah, it's the last comment. Yeah, this one.
What is views text vectorization from TensorFlow? That's great. We haven't tried that. I'm not sure what text vectorization would do. That's a very interesting point. Yeah, I have to look it up. No, thank you for this. We haven't tried. I'm not sure what kind of encoding text vectorization. If it's some kind of random, I guess if it's some kind of randomized embedding where it's a very small dimensional encoding vectors, with high probability that will not be an orthogonal, that will not give you an orthogonal tau. So I think there would be possibility in that case, but I need to check exactly what that encoding does. But thank you for the question. That was the only one? Yeah, okay. Okay, so of course, as usual, when I present this stuff, then I always late on the second part, but here the second part comes about the possibility part, the practical existence theorems. So I'll switch gear a bit. How much time do I have? So I get kind of an estimate of how fast should I go?
10, 15 minutes.
10, 15? Okay, great. I can do that. Okay, so now let's switch gears a bit because this will be a totally different topic. The problem is different. The tools will be different. I will talk about high-level concepts. So I think here it's much easier to get lost, but please do ask questions offline if you want to know more. I'll be really happy to explain things a bit with more time. Yeah, so here the problem is function approximation. We want to approximate a multivariate function. You have a multivariate input x that is mapped to f of x, where x is d-dimensional, d coordinates. You want to approximate this object from pointwise samples. In particular, you want m pointwise samples of f. Personally, my motivation for this kind of problem, that's a very general problem, but my personal motivation is approximation of parametric models. So think about x as some parameters that play a role into a big parametric model that could be, for example, a parametric partial differential equation. For example, you're modeling a diffusion process, and in your diffusion coefficient, there are parameters. Okay, you have this big physical model that depends on parameters that the user might have to tune. And then typically you will need to solve a PDE. So you'll have some kind of black box PDE solver. And typically the task of solving the parametric model might be very expensive. So sampling, so getting the solution to the parametric model, if the physical phenomenon you're studying is very complex, could take even days. I say in fluid dynamics, could be hours or days long simulation. So once you have a solution to your parametric model, then you extract the quantity of interest. Okay, so here the solution m of x is the parametric model, u is the solution to that model that implicitly depends on the parameter 2. Now you just observe something of that solution. Maybe you're interested on the solution in a particular area of the time-space domain, or maybe you're interested in the energy of the solution, whatever quantity you're studying. So this is the f, like you're sampling a parametric model and observing a quantity of interest. But sampling this f can be very expensive. So that's why, because here there's typically a black box solver that will have to be run several times whenever you collect a new sample. So we want to minimize the number of observations here. We don't want to build an approximation that depends on 1 million samples. Maybe you want to be on the hundreds of thousands samples or even less if possible. Okay, so people consider this problem because this is called a surrogate model. You would like to approximate these parameters to quantity of interest model with an approximation of f. And you might use surrogate model in uncertainty quantification, for example. Now, if the parameters are random, then also the quantity of interest will be a random variable. And to study this random variable from a statistical perspective, you need to sample this map many times, okay? But once you have a surrogate model, you can sample much more because the surrogate model would be faster to sample. And this can be applied pretty much anywhere. I'm listing some topics of applications here. If you're interested in the field of uncertainty quantification, that's a book I recommend by Ralph Schmidt, the University of North Carolina, called Uncertainty Quantification, if you want to know more. Okay, how do we build a surrogate, or how do we build an approximation to such a function? Let's assume for simplicity that we are in a hypercube or in a d-dimensional cube minus 1, 1. Then we build a polynomial approximation. For example, that's a classical technique. You might consider orthogonal polynomials. That's kind of classical numerical analysis where you have Legendre polynomials, for example. They constitute an orthonormal basis of the Hilbert space L2 of the hypercube. And then since you're a Hilbert space, everything is nice. You can expand the function with respect to these polynomials. You can even have an explicit formula for the coefficients, just the inner products of your function against the basis functions. But now, in order to be efficient, we would like to generate some kind of sparse approximation. We don't want to compute so we don't want to have an expansion that has a lot of coefficients. We like to have an expansion that only activates a few coefficients. So we're aiming for a sparse polynomial approximation of the function, where the approximated coefficients only have a small number of non-zero entries. And here in this picture, I'm visualizing tensorized polynomials. Okay, so this is how they look like when you tensorize Legendre polynomials, for example. You tensorize constant against constant or linear against constant and so on. Okay, so imagine doing this in very high dimension and using such a basis to represent your high dimensional function. Well, this is in general a very hard task, but if your function is smooth enough, and in particular if it's holomorphic or analytic, then there is hope. Such sparse approximation paradigm could succeed because there's a lot of work being done over the past decade or so, where you can provably show that the best S-term approximation error, when the function is analytic in a so-called Bernstein polyellipse, decays very fast, particularly exponentially, with respect to S to the 1 over D. That's the challenge here of the dimensionality, of course. But here the decay in S to the 1 over D is very fast. You can also prove similar decay rates that are not exponential but algebraic and that are independent of D. So there's an established theory that tells you this is possible if the function is smooth enough. And back to PDE models, PD is like the diffusion equation, the harmonic oscillator, the heat equation, or if you parameterize the physical domain, that will give you a smooth solution map that will allow you to use sparse approximations. How do we actually build the sparse approximation? Well, there's many options. For example, the classical techniques are interpolation via sparse grids. You can do quadrature to approximate the coefficients C by approximating these integrals. You can do least squares. But all these things you can do if you already know what's the polynomial space you're supposed to focus on, which are the basis functions that are more important. In other words, what's the anisotropy of F? Is the anisotropy of F, so how much F is varying in each variable? If F is much smoother in the first variable than in the second variable, then you will have to take more polynomials in the second variable because of the less smoothness. Therefore, it's not trivial to understand how much your expansion should go ahead in each direction. Okay, that's a tricky job. But if you know this in advance, then your anisotropy is known, and you can set up this kind of classical techniques. When you are beyond the known anisotropy case, so unknown anisotropy, these techniques, it's not clear how to apply them because you don't know the search space. Therefore, there are other newer techniques being proposed. One that I will not discuss here is greedy or adaptive methods. Here we'll be talking about compressed sensing and finally deep learning. That will be the end of the talk. So how do you apply compressed sensing to this problem to build a sparse approximation of your smooth function? Well, first, you need to find a quote unquote large enough ambient set, lambda, that hopefully contains the most important coefficient. That's the crucial part. But let's assume for now that an oracle gives us that. An oracle tells you, I don't know exactly where the sparse coefficients are, but there is a largish set where it's very likely that you'll find them. We'll call this lambda. When you expand, then you can only expand F into this lambda set. You sample F with M Monte Carlo samples. You put together a linear system. Now, remember, we want to use much fewer samples, M, than the dimension of this ambient set, lambda, which typically will be very large because the anisotropy is unknown. And so that's why we are in the compressed sensing regime. We'll have an underdetermined linear system of equations that we'll have to solve with some kind of sparse regularization technique. So, for example, here I'm mentioning the square root lasso regularization technique. It has benefits because the optimal tuning parameter here doesn't depend on the noise corrupting the data, which is a very desirable property. But there are other options. This is something more and more refined set of techniques have been proposed in the literature to perform this task, to compute a sparse approximation. And you can also prove a convergence theorem for this. So this works in practice, and we have theory that tells us if you choose, there's a precise recipe on how to choose this large ambient set. That's a so-called hyperbolic cross. That's a classic object in multivariate polynomial approximation. And it looks like that, for example, in 2 dimensions. So if you pick the ambient set as a hyperbolic cross, the compressed sensing scheme will be able to achieve essentially the same approximation rates as the best test term approximation that I showed you before. So that's the best possible achievable approximation rate. Compressed sensing is able to capture that up to the noise norm for the samples. So that's a very, very short introduction to the topic. If you want to know more, there's a whole book about that I co-authored with Ben Atco and Clayton Webster, Sparse Polynomial Approximation on High-Dimensional Functions. I know that's a shameless plug, but check out the companion website if you're curious, sparsehdbook.ca. You'll find much more information. And I'm happy to give you a draft of the book as a PDF if you're interested. Yeah, so back to deep learning. There's a big detour on sparse approximation. What does this have to do? 5 minutes, yes. With deep learning, back to deep learning, there is a thing called the universal approximation theorem that dates back to the 80s. It was proposed by Chibenko, Hornig, and collaborators. That tells you that deep neural networks are universal function approximators. You fix a function class, and then you can prove that there exists a neural network that approximates functions in this class to a desirable tolerance that the user is, to a desirable accuracy that is fixed by the user. Great. Lately, this kind of direction has become very popular. People have generalized this kind of universal approximation theorem to many relevant classes like Sobolev space functions, piecewise smooth functions, band-limited functions, you name it. There's a lot of results on very interesting classes that are used in signal processing and I would say scientific computing. Even the classes of functions that we're caring about here, with these very smooth holomorphic functions, you can prove a universal approximation theorem for that class. However, what does the universal approximation theorem does not tell you is that several crucial things. First of all, is that neural network that is able to approximate this function achievable through training? How much data do I need to train that network? And how does the approximation that I get via deep learning, for example, compares with other approximations like polynomial? So not always these kind of questions are addressed, especially the data question. That's never addressed by a classical universal approximation theory. So that's theorem, sorry. So that's why we put together this result, the so-called practical existence theorem, where now we don't only prove that a network exists that approximates a holomorphic function, but we also give bounds, essentially, we also say something about the amount of data that you need to train it. So now, if you use M uniform samples, essentially we can show that you will be able to train a neural network from a certain class that it's possible to define using regularization that is essentially a sparse regularization on the last layer. And that network then that can be trained by minimizing this regularized loss will have an exponential convergence rate in the number of samples. Now there's an M tilde because there's a technical here, there's technical aspect, there's log factors, but essentially the convergence rate is the same as the compressed sensing convergence rate, which is quasi-optimal with respect to the best S term. And there's also explicit bounds for the depth, number of trainable parameters, and so on of the network. This is the scalar valued approximation. You can also extend this kind of theory when the output is a function. So the output might belong to a Hilbert space or a Banach space, which is relevant where you try to approximate the whole solution of a PD, for example. So high-level idea here is to connect the compressed sensing theory with deep learning approximation theory. Essentially, the idea to construct this network is the first layers will approximate polynomials, and the last layer will learn the polynomial coefficients. That's the high-level idea on how we are able to kind of put together this theorem. In the interest of time, I think I will skip the last numerical experiment too. That's just a convergence of compressed sensing versus neural networks in a parametric diffusion problem. I will just summarize. We have talked about the mathematical foundations of deep learning, inspired as Mail's 18th problem. We have seen two projects where one, the identity effect project, we focus on fundamental limits of deep learning. The second one is more on the positive side, potential of deep learning to approximate high-dimensional functions. Of course, there's much more to be said and done here. And I wanted to mention some of the ongoing research directions with some of my students and postdocs. We are generalizing the identity effect projects to, in the case of noisy encodings, for example, you can generalize the theory there, or to the case of graph neural networks, where it's possible, these are very popular architectures that people are considering these days, and you can prove theoretical results there too. For the high dimensional part, it's possible to generalize that also to when you want to approximate a high dimensional PDs, not a high dimensional function. And also there's two directions. I think that some of the signal processing people could be interested in this, like you can actually do compressed sensing instead of doing compressed sensing with sparsity. You can do compressed sensing with a deep generative model, a priori assumption in recovery. So that's another direction that involves deep learning that I'm happy to talk about offline. And there's another connection between sparse recovery called deep algorithm unrolling, where you interpret the sparse recovery algorithm as each iteration as a hidden layer of your network. And again, that allows you to have new theoretical insights. Okay, so I conclude here. Thank you very much for your attention. And that was a pleasure.
Well, thank you very much, Simone, for this really nice presentation. We have a lot of questions for you. So we can start maybe with the question from the audience first, then back to people online.
Sure.
Okay. So thank you, Simone.
Yeah.
Very nice, interesting talk. That
Thanks.
inspired us. I'm doing signal processing, as you know.
Yeah.
It inspired us to investigate signal processing problems from different angles, deep learning, or for example, comprehensive sensing.
Yeah.
Based approximation. So I have one question regarding the first part.
Yeah.
The tool is very interesting. It plays a very important role. So do you have a very simple example to show what tool does? It's kind of transformation.
Yeah. So
it's invariant to the data set, but
Yeah.
in the meantime, it is variant to a data,
yeah.
right? To a data point in a set.
Yeah. So, I mean, the way I think about tau, that's kind of, it's not easy to grasp what tau, what's the role of tau. The way I think about it is like, after thinking about this stuff for a while now, it's just a device that we use to fool the learner. It's a device that we use to construct a pathological counterexample that will prevent the learner from generalizing. That's kind of the high level way to think about tau. Then, in particular, this is the definition, in the example of the two-letter words. In this case, tau just switches two letters. That's what it does in practice. But at a high level, I think about that as a fooling device,
Okay.
a way to build something that makes life very difficult for the learner.
I see. Okay. So it's going to be used to challenge.
To challenge the learner, exactly. Yeah, because we can probably show that helps us to probably construct an example where the learner is unable to generalize because the rating, which is the output, will always be the same for tau x and x. So here's the counterexample.
Thank you. The second question is regarding V. So you have like W, which is kind of linearly related to X.
Yeah.
The V is like a standalone variable. Is that
V can be anything. So that's the notation that I'm using to in the neural network example. For
kind
example,
of like a bias or
it can be anything. Also bias. In this example, for example, so in the feed-forward neural net, W will just be W0. Is the very first linear operation. All the rest, all the biases and weights for the other layers, they're in V. Just put everything else in V.
okay. So just one more question. For the second part, have you done something like for comparison study for compressive sensing based approximation versus deep learning
Yes.
approximation?
Yes, we have this kind of numerical experiments. That's exactly the purpose that I skipped. Thank you for the question. So maybe I can say something quickly about that. Here we have a parametric PDE problem. So by parametric, I mean the physical domain is 2D, is a diffusion problem in a 2D physical domain, but we have 30 parameters. The diffusion coefficient depends on 30 parameters that the user can fix. So this is a 30-dimensional approximation problem, although the physics is only in 2D, but the parameters is 30. So here we solve this parametric diffusion problem, both with deep learning and compressed sensing. And in the plot, like the solid line is compressed sensing. So here, there's a bit of technical things to notice here. It's a bit of a crowded plot, I know. Maybe let me remove this, the panel. Oh, no. Okay. Whatever. So the solid line is compressed sensing. In the y-axis, in the x-axis is the number of samples that we're using to approximate this object.
Right.
The y-axis is the approximation, the accuracy. Now the accuracy is being measured that's the whole solution to the parametric diffusion problem. So that's the L2 norm in this case. We also measure that in the H1 norm. And the solid line is compressed sensing convergence rate. All the other lines, the dashed lines, are deep learning. So we're combining, sorry, we're trying very many architectures, many activations. Like, for example, here, that's a deep network that has depth 1 and width 10, depth 2 and width 20. So we kind of have larger rectangles for the architecture. We change the activation, that's a ReLU, TAN-H, another thing called leaky ReLU. What we observe in this example, for example, is that now this function is very smooth because that's a parametric diffusion problem. Compressed sensing achieves a good accuracy, but deep learning, essentially, it will depend. If you're not careful with the choice of the architecture, you will do worse. But if you take the right architecture, you can actually overcome compressed sensing. So it's like the theorem tells us that deep learning, in principle, can do as well as compressed sensing. But in practice, if you're careful with the parameter tuning, you can overcome it. But that's where the tricky job of the practitioner will be, like finding this right parameter tuning. So now here we're in a case where we know the ground truth and we measure the error. In real life, we might not have access or recipes on how to do the optimal parameter tuning.
Compressed sensing is like kind of smooth and more robust.
Yeah, I would say so. Compressed sensing in this case would be more robust. You can squeeze out more accuracy with deep learning, but at the cost of a much trickier parameter tuning.
In terms of implementation, which one is better in general?
Well,
Real time, just
in terms of implementation, I would say, I mean, there's a lot of packages for both. So, I mean, there's available open source packages for both. In terms of training the deep network, of course, it's very difficult. So that's the main bottleneck. Students who are working on deep learning related projects are very aware of this fact. Get them to converge can be really, really tough. You have a lot of, kind of empirical recipes that you have to do, because again, the hyperparameter tuning problem is a hard one. So getting the things just right for everything to converge can be difficult. With compressed sensing, in my experience, that's not a big challenge.
Thank you very much.
Thank you. Just maybe a question about because if I have this kind of figures,
yeah,
I would like to apply a compressed sensing first.
Right.
So
me too.
Yeah, me too. Okay. Then regarding the value of compressed sensing, I try to turn the parameters of the deep learning.
Right.
So and I have kind of reference. So I should be under the curve.
Yeah.
Regarding those parameters. Is there any strategy combining both?
Well, in a way, our theory, there are hybrid strategies. So our theory, in a way, it's already a hybrid thing because we are connecting compressed sensing and deep learning to develop the theorem. We haven't tested this much in practice because now we were training the architectures, not with this particular regularization. We were doing just standard training. You could actually consider this type of regularization that comes from compressed sensing. Here, R is just, I can tell you a bit more about the backup slide, about the construction here. The class of networks will be of this form. Essentially, you have the last layer times another family of network that approximates Legendre polynomials. So this network is emulating polynomial approximation. And then how we connect the two worlds is that, okay, we just construct the approximations to the polynomials, and these constructions are available in the literature. And then we just train the last layer. It's kind of a transfer learning, what machine learning people will call it transfer learning, where you have a pre-trained thing, you only update the last layer. And that's at the end of the day, a compressed sensing problem. So I think the potential here to exploit this connection that is just theoretical here in practice, I think it's still unexplored, fully unexplored. So that's a connection that can be done. Also, you can change the prior. If you do compressed sensing, typically you have a sparsity assumption. You can go from a sparsity assumption to the fact that your signal is not sparse in the basis, but is generated by a deep network. So that's called a generative modeling prior. And now you can still use compressed sensing ideas under a deep generative model. So that's another thing way the thing could go hybrid. And that's that direction that started in 2018, actually 17 with Borja Price idea. And we're working on, again, to develop theoretical guarantees for that. But yeah, that's another possibility to have the hybrid.
I have another question concerning the transformation T that you showed us.
Yeah.
And regarding those transformation, so yeah, the learner is enabled to generalize
Yeah.
With permutation, orthogonal basis, and we don't know about the linearly independent. But what about a nonlinear? It seems that if I put a nonlinear transformation. So
that's a good question. I don't have theory for that. That's a great question. But
it seems that okay, the learner has some capability to generalize. So okay, so what about your theory in this case?
Yeah, that's a great question. That's a very challenging one. We have tried to work a bit in this direction, but so far that's the theorem. Like this theorem works because tau is linear. How the theory goes is not that difficult. You just go iteration after iteration in SGD, and you see that essentially this invariance in distribution of the initialization is transferred through the epochs of learning. But that works because this T is linear. If I cannot write a linear transformation here, already that strategy breaks down. So we have tried to think a little bit about this, but I think like a general theorem here is for the moment out of reach. Maybe something could be said for a very specific setting, very specific problem. But yeah, something as general as that in the nonlinear case, I have no clue at the moment. But that's a meaningful challenge.
My last question is concerning the deep learning. I mean, as a tools, and because a lot of people say that this is more philosophical question rather than a technical question.
Right.
So. If we have enough data, so we can, depending on the characteristics of the data, as you mentioned, we can have the capability to generalize, to learn from the data, and to derive low underlying data. That makes sense. But at the same time, people try to compare between the brain and the deep learning, which doesn't make sense from my point of view.
Right.
Because in the brain, we are people like we discover several laws from the universe, from the physiology and whatever, without any kind of data.
Right.
So this is another point of view. If we don't have data, we don't talk about deep learning at all. I mean, there is no way to apply anything to the deep learning without data, because all your theorem comes with invariance on the data set, have enough data set. So let's just come without data. And in this case, there is no possibility having the generalization of anything at all.
Right.
So, but the brain works in a different way. Without data, Einstein was able to generalize.
Right.
A lot of law.
Yeah.
This is the concept of the brain. So the brain is not simply a network. I mean, anatomical and functional network.
Yeah, that was the big debate in the
brain do something else.
Yeah, in the cognitive science community, you were definitely not a connectionist. Then.
So there is this discussion is far from the deep learning. Also, that's why I'm saying it's
the data. If you want, you're right. Without data, there's no deep learning. I mean, we have to think about another setting. Here, the emphasis, though, I think the main takeaway of this kind of theory is that the emphasis, we don't really care about the data here. At least, like, we use the data in the sense that to talk about generalization. Here, we really want to see the learner doing well on something that he hasn't seen before, genuinely. So that's where we use the data. Like, I don't care how much data there's before, but what I want to see here is that the test examples are very different from the training examples. And that difference in this case is measured by the encoding, if you want. Orthogonality tells you that, the test is too different. It's orthogonal to the training. No matter that deep learning is a very nonlinear scheme that cannot break that orthogonality barrier. So maybe, the key takeaway here is, if you break that orthogonality in the encoding, then all of a sudden things become possible. So maybe that tells us something about not like how much data we need, but even just how data or how features should be represented. Maybe in the brain, I don't know, or outside, but it's really about the representation here.
Okay, maybe I'll let other people from the website ask question if there is any. Any question, Dr. Swami, Dr. Ahmed?
No.
Okay. Okay, back to the audience. Any question? So, okay, so let's stop here.
Okay,
So thank you very much, Simone, for
thank you.
this presentation.
Thanks.
Then,
Thanks for
okay.
taking the time to listen to me. Thank you.
Okay.